Okay. So yeah, no new postulates today, not very many new definitions, and only a few theorems actually contributing to the construction of our geometry. So let's first start with that. Let's quickly remind ourselves of our basic congruency theorems from last time. There's three congruency theorems that we had for triangles last time. What are they?
Side, angle, side.
Side, angle, side.
Angle, side, angle.
Angle, side, angle, and
Side,
side, side, side. Those are our three basic congruency theorems for triangles. You're going to be using those left and right. Hopefully your chapter 6 homework gave you plenty of practice using those theorems over and over again in different scenarios, looking for the triangles that you can identify as being congruent to each other. It's a huge part of geometry, is just seeing that. Okay, so first definition here. If an angle is adjacent and supplementary, so adjacent meaning next to, what does it mean for two angles to be, what does it mean for an angle to be supplementary to another angle?
That their angles make a straight angle.
That their angles together make a straight angle. So if an angle is adjacent and supplementary to an angle of a triangle, it is an exterior angle, and the other two angles of the triangle are exterior opposite angles. What is that saying? This angle right here is an exterior angle to triangle ABC here. It's adjacent to it, and it's supplementary to one of the angles. Right? I could have just as easily made an angle up right here, and that would also be an exterior angle. And I could have made one over here, and that would have been an exterior angle. I picked the one over here. Good so far? So there isn't the exterior angle of a triangle. There's many exterior angles of a triangle. Here's one of this triangle's exterior angles. The two angles opposite this angle, what angles are opposite this angle in the triangle?
Angle A, angle B.
Angle A and angle B are called the opposite interior angles of this angle. So once you pick an exterior angle, it has two opposite interior angles. Angle A and angle B are the exterior opposites of this angle right here. With me?
Yeah.
Just a definition. Okay, so our first proof here is going to be that an exterior angle is always bigger than either of its interior opposite angles. I'm going to prove that this angle is bigger than angle B and it's bigger than angle A. You with me?
Yep.
Now in our proof, all I'm going to prove is that it's bigger than angle B. You can reconstruct the proof, proving that it's bigger than angle A in the exact same way. So we're only going to show that this angle right here is bigger than angle B, no matter how you draw the picture. Okay? Here's how the thinking for the proof is going to work. First thing I'm going to do is I'm going to come over here and I'm going to find a point D. And I'm going to find D such that this side length is congruent to this side length. You with me? And now, look at this triangle. What do I know about this triangle compared to this triangle?
They should be congruent.
No, they're not going to be congruent,
Oh, right.
but they're going to have this side length in common. And what else do they have in common? This side length. You with me?
Yep.
So the way that I'm going to prove that this angle is larger than this angle is I'm going to show that this angle can't be congruent to this angle, and then I'm going to show that this angle can't be smaller than this angle. And if it can't be congruent and it can't be smaller, then it must be bigger. So first we'll handle the congruent case. So what if this angle were congruent to this angle? So now impossible picture. Pretend that those two angles are congruent.
Then the triangles will be congruent.
Then the two triangles are congruent, right?
On side, angle, side.
And so we know that this angle here is congruent to which one? What's this angle congruent to? Is it congruent to the one up here or the one down here? Top or bottom?
Bottom.
Bottom?
Wait.
Which triangle is congruent to which triangle? Let's write it out. Triangle, tell me what triangle ABC is congruent to. ABC is congruent to what triangle?
E.
What's the order here? Tell me what letter comes first.
E. E.
No, D comes first. Side, angle, side.
Oh, you constructed it to D. I thought you constructed.
Yeah, right.
DC is the same as AB.
Right.
Yeah.
Okay.
BC is the same as CB. So triangle ABC is congruent to which triangle?
DCB.
DCB. You see that?
Got it.
It's not BC.
No.
It's not BC.
Yeah,
No.
yeah, okay.
We're doing the side, the point that has the angle, the side.
Yeah.
The side, the point that has the angle, the side. Side, angle, side. By side, angle, side, those two triangles are congruent. So, this angle is congruent to which angle? Top or bottom?
Top.
It's congruent to the top angle. Now, what is the angle sum of these two angles?
Straight angle.
Straight angle, right?
Yeah.
So what's the angle sum of these two angles?
A straight angle.
Should be straight in.
Straight angle. So what do I know about points A, B, and D?
They're collinear.
They're collinear.
Wow.
And how do I know that that's impossible? For A, B, and D to all lie on one line.
You constructed it not like that?
It's a triangle.
It's a
I don't know.
triangle. ABD is collinear. How do I know that ABD can't be collinear? How do I know I can't draw a line through A, B, and D? What would that line
It
do?
would intersect.
It would intersect this line twice.
Right.
Okay.
You see it?
Yes, yes.
So that is the heart of the proof. So let's reset that up one more time. Oh, not erasing that, erasing this. And now set up the picture for you. So let angle BCE be an exterior angle of triangle ABC. So just set up my picture so far. We haven't picked the point D yet. Let D on the ray through CE such that CD is congruent to AB. So now I've set up the picture so far how we have it. Good? Okay. Assume, by way of contradiction, that angle BCD, our exterior angle, is not larger than angle B. And if it's not larger than it, what must it be?
Either.
The same big or smaller. Congruent or smaller. Perfect. So let's handle the case where it's congruent and see how it gets us a contradiction. If angle BCD is congruent to angle B, so if this angle is the same big as that angle, then triangle ABC is congruent to triangle DCB by side angle side. Right? All right. So then angle C is congruent to angle CBD. Angle C is congruent to angle CBD. And so angle ABD is what?
A straight angle.
Is a straight angle. Perfect. So then two lines intersect at the points A and D. Right? We have this line through A and D, and then we have this line through A and D. Two lines intersect at the points A and D. Contradiction. Two lines can intersect at most one point. All right, now we need to handle the case. Okay, so these two angles can't be the same big. How do I know that this angle can't be smaller? So let's set it up again. This time, let's assume that this angle is smaller than this angle. What do I know if this angle is smaller than this angle? What does it mean for one angle to be smaller than another angle?
It fits inside the interior.
You can fit the smaller one inside the bigger one, right? So that would mean that we can find some point here. I think I called it F. That would mean we can find some point here, F, such that angle CBF is congruent to angle BCD, right? If this angle were smaller than this angle, then I could inscribe some angle inside of there, such that this angle is the same big as that angle. So now we got that this angle is congruent to an exterior opposite. But the first part of our proof was showing that that was impossible. So we already handled the case that an exterior angle can't be congruent to one of its interior opposites. So we're done. So, continuing now, right here. If angle BCD, that's our exterior one, if angle BCD is less than angle B, then there must exist F on segment AC, must exist F somewhere between A and C, so it's on the segment AC, such that angle CBF is congruent to angle BCD, our exterior one. then angle BCD is exterior to triangle CBF. Here's triangle CBF. Angle BCD is an exterior angle and is congruent to one of its interior opposites. We already proved that that was impossible in the first case that we handled. So it can't be less than, or it can't be congruent, it can't be less than, therefore it's greater than. That's the thinking for that proof. All that makes sense? Okay. Next one of the more famous theorems in, oh, no, that's not this one yet. That's not here. Next one, we're going to show that in a triangle, pick any triangle you want, ABC, the biggest angle is always going to be opposite the longest side. The longer this side is, the bigger the angle opposite is going to be. The longer this side is, the bigger the angle opposite it is going to be. And the longer this side is, the bigger the angle opposite it is going to be. So the biggest angle is always opposite the biggest side. Make sense? That's what we're going to prove. We're going to prove that in triangle ABC, if side length AB is greater than AC, then angle C, the side opposite, notice that angle C is opposite side AB. It's using the letter that this side didn't use. What angle is opposite AB? Angle C. What angle is opposite AC?
B.
Angle B. The letter it didn't use is the angle that's opposite it. So, if AB is greater than AC, angle C is greater than angle B. We're going to do this as an if and only if. I'm going to show that if the side length is bigger, then the angle is bigger. And then I'm going to show that if the angle is bigger, the side length is bigger. Make sense? Okay. So, how are we going to do this picture? So let's go the first way. Let's assume that AB is greater than AC. Now what does it mean for AB to be bigger than AC? What's its definition?
AC can fit, maybe?
Yeah, there must be some point over here, C prime, such that this is congruent to that. You with me? Okay, so now I've got this triangle right here.
Isosceles.
Well, it's an isosceles triangle, so I know that this base angle is congruent to that base angle. Yes. Okay. What angle am I trying to show is bigger than what? I'm trying to show that angle C is bigger than angle B, right? Okay. First off, notice that angle C is definitely bigger than this piece of angle C, right? And this piece of angle C is the same size as this angle over here, because this is an isosceles triangle. And how does this angle over here compare to angle B?
It's bigger than angle B?
How do you know?
I don't know how I know.
Over here. This is an exterior angle to this triangle. So it's bigger than either of its opposite interiors. So I have angle C is bigger than this angle, is the same size as this angle, is bigger than angle B. Therefore, angle C is bigger than angle B.
That's cool.
You follow that thinking?
Yeah.
That's what we're going to explain here. So assume AB is bigger than AC, then there must exist some point C prime in the segment AB such that AC prime is congruent to AC. Just setting up that exact picture we have there, right? Then AC prime
Did you mean C prime C?
Thank you. A C prime C is exterior to triangle BCC prime. And so angle B has to be less than angle AC prime C. Right? Then angle C is for sure bigger than ACC prime. Should have done one more step here. Angle C, this whole angle, is for sure bigger than ACC prime, is congruent to angle AC prime C, is bigger than angle B. Angle C is bigger than angle ACC prime, is congruent to AC prime C, is bigger than angle B.
Oh my
the day I look at all this stuff on the board. That's so cool. And good handwriting. I mean, what?
Thank you.
What? Are you missing people today?
Do not think so.
Sweet.
We're all here.
That's awesome. Thank you for being here.
Thank you.
Wow. Hey, will you guys make sure you don't get mixed up on that board?
Go ahead.
I want to let you know that I have to leave at 9:50 for a dentist appointment.
Just for you, I'm going to record the rest of the lecture. Okay, no worries. Just feel free to walk out when you need to. All right, so we got that angle C is greater than angle B, what we were after. Woot, confetti. Next, we need to show the other direction. This time we're going to assume angle C is bigger than angle B. So let's reset up our picture here. And this one we're going to prove kind of like our other proof, the second part of our other proof. Assume angle C is bigger than angle B. So assuming this angle is for sure bigger than this angle. Now what do I know? Well, let's not say that. What am I trying to show this time?
AB is greater than AC.
I'm trying to show that AB is greater than AC. That's what I'm at to prove. I need to show AB is greater than AC. Now, I'm going to show, the way I'm going to show it's greater, is that I'm going to show that AB can't be congruent to AC, and AB can't be less than AC, therefore it has to be greater than.
Okay.
What would happen if AB was congruent to AC? How would these two angles compare?
They'd
They
be
would be
congruent
the same.
because it'd be an isosceles.
They'd be congruent, because it'd be an isosceles triangle.
Right.
So, I know that AB can't be the same big as AC. What would I know if AB were smaller than AC? What would I know about these two angles? If AB was less than AC, what would I know?
That angle B would be bigger.
Using the first part of our proof here, if AB is smaller than AC, then that would mean angle C is smaller than angle B. But I know angle C is greater than angle B. So it can't be the same big, it can't be less than, therefore it has to be greater than. Go ahead.
Are most of the proofs in this chapter going to be contradiction, like true?
Proof by contradiction.
Proof by contradiction.
There's no way to see that ahead of time. And you never really have to use a proof by contradiction. There probably is a constructive way that we could have done this. It's just, you saw that I can somehow use the first part of the proof again, and so I don't need to go reconstruct some picture.
Yeah.
And that can happen somewhat commonly in if and only if proofs.
Okay. Yeah, that makes
Okay.
sense.
Okay, so let's walk through exactly what we just said this time. So now let's assume that angle C is greater than angle B. We're trying to show that AB is greater than AC. The way I'm going to show that is AB can't be congruent to AC, and AB can't be smaller than AC. Therefore, AB has to be greater than AC. So if AB were congruent to AC, then angle B would have to be congruent to angle C, because we have an isosceles triangle. So the base angles would have to be congruent. Contradiction, because I know angle C is bigger than angle B. Next, if AB was less than AC, we showed that the angle opposite this is less than the angle opposite this. Plus the angle opposite AB,
C.
angle C, is less than the angle opposite this.
Angle B.
Contradiction, because we know C is greater than B, this is saying C is less than B. So it can't be greater, so the two legs can't be congruent, AB can't be smaller, therefore, ignore that. Therefore, AB has to be greater than AC. There it is. Good?
Yeah.
Okay. Next one, and our last major proof of the day, the triangle inequality. Here's the somewhat famous one, probably the second most famous proof from geometry. I don't know. We're going to prove that in any triangle ABC, that the length of two sides is always greater than the length of the third side. It's impossible to construct a triangle so that one side is longer than the other two sides add together. Intuitively, what this proof is giving us is that the shortest distance between 2 points is a straight line. You can't take some jag and make your distance shorter. Make sense? That's intuitively what it's giving us. So I'm going to prove that for any triangle, the length of AB plus the length of BC is greater than the length of AC. Okay, so we're going to pick some arbitrary triangle ABC. Now notice right out the door, this is obviously true if AC isn't the longest side. If AC isn't your longest side, it's obviously the case that one of the longer sides plus more length is going to be greater than AC.
Why do we have to use the length of segments? Why don't we just use?
Just so I can treat them as numbers and add them together.
Okay.
We don't have a good way of adding in talking about congruency language. I'd have to talk about somehow constructing the segment and then constructing it adjacent to it on the same line, and it could get a bit annoying.
Could we do it without talking about length?
Yes, you could do it without talking about length. How could you do, because length is logically equivalent to congruence. You would just have to keep constructing your segments in one line, rather than just taking that length and adding it to that length and comparing it to that length.
Okay.
So, easier to deal with numbers. Okay, so in triangle ABC, the length of AB plus the length of BC is greater than the length of AC. Now, if AC is less than or equal to the length of AB, or AC is less than or equal to the length of BC, we're done, obviously. If AC is not your longest side, this is obviously the case. If this number is greater than or equal to this number, then obviously this number plus this number is bigger than that number. Furthermore, if this number is greater than or equal to that number, then this number plus this number is obviously greater than or equal to that number. Remember, all distances are positive numbers, or 0. So by adding these two together, we couldn't have made anything smaller.
Right.
So take some distance, which is greater than or equal to AC, add some more to it. Obviously, it has to be more than AC. Make sense? So if AC isn't the longest side of the triangle, we're obviously done. So now we need to handle the case where AC is the longest side of the triangle. It's the only interesting case. Good? Okay. So now let's handle the case, and let's assume that AC is greater than the length of AB, and AC is greater than the length of BC. Now we're going to construct our triangle. It doesn't matter which one we use. Let me see which one I used here. Let D on AC such that AD is congruent to AB. Okay, I made it congruent to AB. So trying to draw a somewhat accurate picture here. So I'm going to choose D here such that this length is congruent to that length. And so we've got that isosceles triangle right there, right? Okay. What am I trying to prove? I'm trying to prove that this distance is less than this distance plus this distance. You with me? Now, how does this distance compare to this distance? They're the same. So all that remains to show is that this is more than this. And if I can show that this is more than this, we're done. Right?
Yeah.
Now, showing that this is more than this is the same as showing which angle is bigger than which angle.
BDC is bigger than...
BDC, I need to show that BDC, this angle is bigger than which one?
Angle C or angle B.
But in our particular case, if I'm trying to show that this length is bigger than this length,
It's
Angle B.
then this angle is bigger, not angle B, but you've got the idea, this portion of it, right?
Yeah. Oh yeah.
Okay. Now finally, look at our triangle on the left. What kind of triangle is it?
Isosceles.
So what do I know about its base angles?
They're congruent.
They're congruent, perfect. So this angle is congruent to this angle. Can you guys see all three of those lines okay?
Yeah.
Yes.
Let me just make this a solid line. I think the dotted line is adding confusion. Okay. So all we need to show is that this angle is bigger than this angle, and we're done. Now, how does this angle, angle BDC, how does this compare to this?
Is it supplementary?
Yeah.
Supplementary.
Notice that this angle right here is an exterior angle to the triangle on the left.
Okay.
So it's bigger than either of the opposite interior angles. So I know this angle is bigger than the one over here. More importantly, I know this angle is bigger than this angle. And this angle is the same big as this angle. And this angle is bigger than this angle. Because this angle over here is an exterior angle to this triangle.
Okay.
You see that? You are bigger than you are as big as you are bigger than you.
So.
Therefore, you are bigger than you.
Yeah.
Therefore, your opposite side is bigger than your opposite side. See it?
Okay. Yeah. No, that actually makes a lot of sense.
All right, so let's restate our thinking. So we pick D on segment AC such that AD is congruent to AB. So AD is congruent to AB. How did I know that D would lie on segment AC? How do I know that D wouldn't go past it?
Because
You
D is
established that
AC
AC is
bigger.
bigger than.
Right, because I know that AC is bigger than AB. What does it mean to be big, one segment to be bigger than another? It means that when you pick the point that makes it congruent, then it's going to lie in between them. Okay, perfect. So, now get this out. So then, angle BDC, this is going to be our biggest angle. Angle BDC is bigger than angle ABD, one of our isosceles triangles base angles, is congruent to ADB, our other isosceles triangle base angle, the one down here, is greater than its interior opposite. So we got angle BDC is greater than angle DBC, which means that the side opposite point D is bigger than the side opposite point B. So what was the side opposite point D? BC. We're looking at this triangle. So the length of BC is greater than the length of DC. Now I'm going to add the same distance to both sides. So I know BC is greater than DC. Add the same distance to both sides. If this inequality is true, if I add the same thing to both sides, the inequality still holds. So, add the same thing to both sides. On this side, I added AB, which is the same thing as adding, or I add AB to one side and AB to the other, which are both the same length. So to BC, I add AB, this length, and to DC, I add AD, this length. But these two lengths are the same, so I add the same thing to both sides. And what is AD plus DC?
AC.
AC. So therefore, this side is greater than this side, which is AC. Good?
Yeah.
Any questions on that? Okay. Quick corollary that follows from that. Pick any points, 3 points you want, A, B, and C, and it's always the case that the distance from A to B plus the distance from B to C is less than or equal to the distance from A to C. Notice over here, or down here, it was always less than. Over here, now if you pick any 3 points, it's less than or equal to. How do we get the equal case? How can I pick-
Triangle.
Huh?
Equilateral triangle.
Equilateral triangle? No, that still doesn't give it to me. If I have an equilateral triangle like that, then the distance from here to here plus the distance from here to here is not equal to the distance from here to here. How can I pick 3 points so that the sum of the distance between
They're all
doing two of them,
They're called
collinear is the one case. So triangles, we can't have collinear cases because it's a triangle.
Right.
If you have 3 collinear points, you don't have a triangle. If, however, I had my points like this, all collinear, this was a point A, this was a point B, and this was a point C, then notice that AB plus BC is exactly equal now to AC. So that's where the equals comes from. So for a triangle, AB plus BC is always less than, or is always greater than AC. But for any 3 points, the distance from AB plus the distance to BC is always greater than or equal to. Wrong way. Don't let me make mistakes like that. Which is what we mean by the shortest distance between 2 points is always just the line segment that connects them. It's impossible to go across 2 different line segments and it's impossible to find a shorter path. Pick any 2 points, the shortest distance between them is always the segment that connects the points. There is no shorter path. That's what it says. Okay. Now, the triangle inequality, it has a counterpart that you may have come across in algebra. So I'm going to give you the algebraic triangle inequality. This has nothing to do with the book. This is just to give it to you, because it's one you've probably come across already. Let's remind ourselves of the absolute value function. What's the absolute value of x? It spits out x if x is greater than or equal to 0, and it spits out negative x if x is less than 0. What's the absolute value of 3?
3.
Using the definition, let's see, is 3 greater than or equal to 0?
Yeah.
So since what we plugged in is greater than or equal to 0, spit out whatever we plugged in. That's what this says to do. What's the absolute value of negative 3?
3.
Is 3 greater than or equal to 0?
Yeah.
Or sorry, is negative 3 greater than or equal to 0?
No.
No, so we're using this case. Is negative 3 less than 0?
Yes.
So that means spit out the negative of whatever you gave me. And so it's negative 3, which happens to be 3. Okay, fine. But it's negative 3. Algebra students often get the simple-minded notion, just drop the negative sign, which can get you into trouble. How can that just get you into trouble? It can't really. Alright, so now, just make sure you get it. If a is less than 0, then what's the absolute value of negative a? It's just a, right?
Just A.
Yeah.
No!
No, it's negative.
It's negative a. You cannot just drop the negative signs. I just told you that. That told you I was lying. Now I'm telling you again. You cannot just drop the negative signs.
It's negative.
That will get you into trouble. You have to think about your definition. Let's see. A is a number less than 0. Right?
Yeah.
Let's plug it into our function here. Is a greater than or equal to 0?
No.
Oh, sorry. We're looking for the absolute value of negative a. Restart. Plugging in. So if a is less than 0, what's negative a?
Greater than 3.
Greater than 0. So let's plug it in. Is negative a greater than or equal to 0?
Yeah.
Yeah, then you just spit out whatever you plugged in. So we plugged in negative a, we spit out negative a. Because a was already a negative number.
Right.
It's exactly what we did with negative 3. A here could have been negative 3, so if I asked you what's the absolute value of negative 3, what is it?
Negative 3. Negative 3. Wait.
3.
What's the absolute value of negative 3? It's just negative 3. Here's our a. What's the absolute value of negative a? It's negative a, which happens to be 3. You could do that with the 3, but now with the a, you didn't have two negatives to cancel out.
Okay.
So don't be simple-minded and just drop your negative signs. Think about the definitions of things. Go ahead.
Do you need to finish the bracket right there, or is it like
I missed a bracket.
Under definition.
On your
in the
definition.
definition?
Oh, my definition. Oh, you're saying right here?
Yeah.
No, that's how you write it.
Okay, not at the end either.
You can put a comma there.
Okay.
But that's how you define piecewise functions.
Okay.
Okay, so now that we've got you thinking about the definition of absolute value, some quick lemmas. I'm not going to bother proving these. A lemma is a small proof you do to build up to the main proof you're trying to prove. So lemma: x is always less than or equal to the absolute value of x is always less than or equal to the absolute value of x. Now, how would you prove this? Just do the positive and negative case. What's the absolute value of x? It's either x or negative x, and just show in either case it's going to be greater than or equal to x. If x is negative, then you have a negative number is less than or equal to the negative of a negative number, true. And then if x is positive, it's just equal. So that gives you the equal case. So if x is negative, it's going to be less than. If x is positive, they're going to be equal. There's your less than or equal. Next lemma. The absolute value of x is always equal to the absolute value of negative x. Again, that's a simple proof. Just handle both cases. Handle the case where x is some number greater than or equal to 0. Now handle a case where x is less than 0. Holds in both cases. Now the actual triangle inequality. Here's what it is from algebra. It's the absolute value of a plus the absolute value of b is always greater than or equal to the absolute value of a plus b. Now remember, absolute value gives you, like, you can think about as one-dimensional distance. So similar idea here. So absolute value of a plus absolute value of b is greater than or equal to the absolute value of a plus b. The distance you go to a plus the distance you go to b is greater than or equal to the distance you go to a plus b. Remember, b could be a negative number here, so a plus b isn't necessarily equal to the absolute value of a plus the absolute value of b. Let's think of a concrete case where we plug in 3 here and negative 2. What's the absolute value of 3?
3.
What's the absolute value of negative 2?
Negative 2, so 2.
Add them together.
5.
What's 3 minus 2? 1. 5 is greater than or equal to 1. So there's a case where they're not equal. A case where they're equal is when both these have the same sign. So now if I plug in 2 for b, then we get 3 plus 2 is greater than or equal to 3 plus 2. Where 5 is greater than or equal to 5. Okay, so let's quickly prove this. So let's look at the absolute value of a plus b, just looking at its definition. What is the absolute value of a plus b? And here's what I meant in both these proofs, just handle both cases. The absolute value of a plus b is either if a plus b is a positive number, if it's greater than or equal to 0, what does it spit out? If a plus b is greater than or equal to 0, it just spits out a plus b. If a plus b is less than 0, it spits out negative a plus b, or negative a plus negative b. The absolute value has to spit out one of those two things. That's all it can spit out. And now I'm going to show that in both cases, the absolute value of a plus the absolute value of b is greater than or equal to the absolute value of a plus b. So absolute value of a plus b, it has to be this, or it has to be this. That's all the definition allows for. Those are the only two cases. Handle each case. So let's look at a plus b. I know that a is always less than or equal to the absolute value of a. That's using this lemma. And I know that b is less than or equal to the absolute value of b. So I get a plus b is less than or equal to the absolute value of a plus the absolute value of b. And now look at negative a plus negative b. A number is always less than or equal to its absolute value. A number is always less than or equal to its absolute value. So this plus this is less than or equal to its absolute value plus its absolute value. But the absolute value of negative a is the same thing as the absolute value of a, and the absolute value of negative b is the same thing as b. So what did I show? I showed a plus b is less than or equal to the absolute value of a plus the absolute value of b. And I showed negative a plus negative b is less than or equal to the absolute value of a plus the absolute value of b. These were the only two values that this function could spit out. This absolute value of a plus b was either a plus b, in that case it was less than that, or absolute value of a plus b is negative a plus negative b, which is still less than or equal to that. So I handled the two cases. I handled the top case right here. I handled the bottom case right there. Tried to keep them on separate lines so that you can see top, top, bottom, bottom. And in either case, the absolute value of a plus b came out to less than or equal to the absolute value of a plus the absolute value of b. Pretty straightforward proof. Good? Triangle inequality from algebra. Okay, for these next definitions, let me move my camera first. Don't worry, just a bunch of definitions. We don't have any more hard proofs ahead of us. Okay. Definition. Our next definition is going to be of a polygonal path. What's a polygonal path? Pick a bunch of points in the plane. Whichever ones you want, doesn't matter. Just order them. So call your first point P1. Pick some other point, and what are we going to call it? P2. Pick some other point, what are we going to call it? P3, and keep going, picking points, and do that n times, where n is some number. 5, 10, 100, however many times you want. This is going to create, so now I'm going to construct all the segments following that order. So connect P1 to P2, connect P2 to P3, P3 to P4, I can't remember how I did it. Pretend it went like this. Okay, there's that figure. A bunch of segments connecting a bunch of points. That's called the polygonal path. Pretty simple definition. Here it is in writing. Let P1, P2, Pn be n points. Then the segments P1 to P2, together with P2 to P3, together with P3 to P4, Pn minus 1 to Pn. So here's Pn minus 1. Here's Pn minus 2, etc. So those we call a polygonal path. Now we could have had the special case where, wish I didn't label all those. Pretend that was Pn minus 3, that was Pn minus 2, this was Pn minus 1, and then Pn was actually happened to be the exact same point that we started at. That could happen. If your endpoint and your start point happen to be the exact same thing, we now have what we call a polygon.
Is n a finite number every time?
Yeah, n some finite number. 10, 100, 1,000, whatever. So then we get some polygon. And we call these points of our polygonal path, we call those vertices. And when we have a polygon, we call each of these segments the sides of the polygon. Now that's a very hideous polygon. You're used to more standard polygons. Something that looks like this. Not crisscrossing with itself all over the place. There's another polygon. Triangle's a polygon. Question, is this a polygon?
No.
No, because the start point and the end point aren't the same. But if it was connected, now for sure the start point and the end point are the same. Which one's the start point and the end point? I don't know, but it doesn't matter since it's closed on itself. At some point, the start point and the end point had to be the same.
What if the point n minus 1 goes back to the start, but the point n goes beyond? Would that still be?
So if your start point and your end point, something like that, now it's not necessarily a polygon.
Not necessarily.
There's probably a way of thinking about that as a polygon. You'd have to have a bunch of points coinciding. So you could have that this was P1, here's P2, here's P3, P4 happened to land on P2, here's P5, here's P6. There's a lot of very degenerate polygons you can make that we don't really like working with. And you know the standard polygons that we're used to working with. Just definitions. Obviously, we're not interested in just any random polygonal structure you can throw out there. We're interested in particular ones.
So polygonal paths are allowed to intersect.
Polygonal paths can intersect themselves left and right. Polygons can intersect themselves left or right. And we have names for other polygons that behave more nicely, like convex polygons. Which we're not getting into in this chapter yet.
By the way, are we doing absolute values in this chapter either, or is that
No,
just?
that was just a side note from algebra that same name to a theorem that we just covered. And it's saying here, very similar to exactly what we were saying up here for any 3 points.
Okay.
Just showing you this compared to this. Oops, this. Very similar ideas. Anyways, forgot to talk about the length of polygon path. So let's draw up some polygonal path up here again. So here's P1. Pick some other point. Here's P2. Here's P3. Here's P4. Dot, dot, dot. Here's Pn. Okay, so we got some polygonal path here. The length of the polygonal path is exactly what you would guess it is. It's the length of this segment plus 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 the length of that segment. So the length of the polygonal path, P1 to Pn, is the length of segment P1 to P2 plus the length of segment P2 to P3, dot, 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 to Pn minus 1 to Pn. Good?
Should that be definition 7.3?
Good chance. It could have also been a continuation of definition 7.2, but I'm guessing you're right. Okay, quick corollary that instantly follows. The length of our polygonal path is always greater than or equal to the length of the segment going straight from P1 to Pn. So following the path is always longer than or equal to the length of just going directly from P1 straight to Pn. How would we prove that? This would use a proof by induction, which you guys haven't come across yet. It's a simple proof style. You just haven't used it yet, so unfortunately we can't completely prove it. But the proof idea is we can remove a point from a path over and over again. So notice that, starting out with our initial path, say I cut out point 2 and I go straight from point 1 to point 3. And so I don't take this path. I had to have made my path shorter or kept it the same length. I couldn't have made it longer doing that. How do I know that? Triangle inequality. Now, look at the next point. I'm going to cut P3 out of my path. I'm going to go straight to P4. Could have only made my path shorter. Now I'm going to cut P4 out of my path, go straight to P5. Could have only made my path shorter. Now I'm going to cut that out and go straight there. Could have only made my path shorter. So you keep seeing the triangles over and over again, making it shorter and shorter down to your straight line segment. Good? That's the proof I did. To actually prove it requires proof by induction, which you guys don't know yet. So we can't do it. But that's the proof I did. Okay, next definition, pretty straightforward. A circle is determined by some point O, which we call the center of the circle, and a positive number R. Okay? For any point A, if the distance from O to A is equal to R, then A is on the circle. So R is some positive number. We could think about a concrete case, R equal to 5. And O could be that point. What is our circle? It's a set of all the points A such that the segment from O to A would have length 5. Make sense? If the distance from O to A is greater than R, then we say that A is in the exterior of the circle. So if we pick some point out here, I'll use B instead of A since we have A right there. If I pick some point out here, B, and the segment OB's length is more than 5, B is in the exterior of the circle. And similarly, if I pick some point B here, such that the segment OB is less than R, then we say that it is in the interior of the circle. Question, is this point on the circle?
No.
No.
Now, is this point?
Yes.
Is this point?
No.
That's it.
No. Is this point?
No.
No. The points on the circle are the set of all the points such that when you construct their segment, it has a length of 5. Those are the ones on the circle. If the segment length is less than 5, it's in the interior of the circle. If the length of the segment is more than 5, it's in the exterior of the circle. Pretty straightforward definitions, right? If A and B are 2 points on the circle, A and B are 2 points on the circle, and their segment contains the point O, we call A and B a diameter. We call any of the segments O to a point on its exterior, O to some point A out here. Could have been that point, could have been to that point, could have been to this point. We call these
A radius.
a radius. So those are radii. How many radii does a circle have?
Infinite.
It can have infinitely many. There isn't the radius of the circle. Question, is the radius of this circle 5?
Yes.
Yeah.
I
The
don't
length of the radius is
know.
6.
Of this circle. Is the radius of this circle 5? I told you r is equal to 5. Is the radius of the circle 5?
The length of the radius is 5.
The length of the radius is 5. We use lazy speech. We say this circle has a radius of 5. Technically, a radius is a geometric object. It's a segment. So when we say the radius of the circle is 5, we really mean the length of the radius is 5. Now, nobody uses that precise of language, and everyone says the radius of the circle is 5. Go ahead.
Wouldn't that mean that on the definition it has to be congruent to R?
No, because r is a number. You aren't congruent to a number. We don't have a segment is congruent to 5. We have 2 segments are congruent to each other. So segments are congruent to segments. Numbers are equal to numbers. And so the definition would be that the length of the segment, which means we now have a number, is equal to r. So we talk about numbers being equal to numbers. We talk about segments being congruent to segments. That good?
Yeah.
Okay. Any other questions about that? So what's the radius of the circle?
The length of it is 5.
Yeah, but what's the radius?
It's OA.
It's any segment between O, the center of the circle, and a point on the circle.
Yes.
That's a radius. Okay. And then obviously, what is the length of the diameter?
2R.
2 radiuses. Because it's the length of that radius plus the length of that radius. So the length of your diameter is always equal to 2r. More terminology. Pick any 2 points on a circle. I think I call them E and F here. E, F. Anyone know what this segment is called? That connects 2 points on a circle?
I should know this.
Yes.
It's called a chord.
That's right.
So that is a chord. And a line that goes through a chord, do we know what the line that goes through a chord is called? A secant line. So a tangent line, you might remember, a tangent line would intersect the circle at 1 point. A secant line goes through 2 points. So if E and F are points on the circle, then, that was an E to my picture. Here's my picture. Then EF is a chord, and the line through EF is a secant. Central angle. What's a central angle of a circle? Let's erase some of our picture here. So I've got some circle here centered at O. A central angle is an angle whose vertex is O. So here's a central angle. Now I drew that picture a little bit misleading because an angle is composed of 2
Rays.
rays. And how long is a ray? Infinitely long. As a matter of habit, we usually just end the ray wherever it intersects the circle again. But keep in mind that the ray does go on forever, so to speak. We just never draw them that way. Okay? And then finally, we have an inscribed angle. What is an inscribed angle? It's an angle where the vertice lies on the circle. So not at the middle. The vertice lies on the circle. So we'll draw it down here. So here's going to be my vertice. It's a point on the circle. And the two edges, and the two sides of the angle intersect the circle. So here is an inscribed angle, because both its sides intersect the circle, and its vertex lies on the circle. Here is not an inscribed angle. Its vertex lies on the circle, but its sides do not intersect the circle, except at the vertex. We mean it intersects at a point that's not the vertex.
So the sides have to be chords?
They're not chords, because remember that they go on forever. But you see how they contain chords within them.
Yeah.
Good. All right, so exact definition. A central angle is one whose vertex is O, the center of the circle. An inscribed angle is one whose vertex lies on the circle and whose sides intersect the circle, not at the vertex, at a point other than the vertex. Good? All right, there's our definitions. Now, we are going to take a step away from our geometry for a second. And we're going to jump into Euclid's world. Stepping away from our geometry. So our geometry, so far we have introduced to you 17 postulates and a whole lot of definitions and theorems, right? We'll kind of piggyback on some of our definitions or rely on your intuition here. But I want to introduce you now to Euclid's elements, to Euclid's world, to the way that geometry was done for well over 2,000 years. Because you might have noticed in like some sort of pop culture reference to geometry, they're always using these things called straight edge and compasses. We've done a whole lot of geometry, and we have done nothing with straight edge and compasses. Rulers and compasses are sometimes called RC constructions. So we're going to get into RC constructions. That's a part of this chapter. But why on earth are these such a dominant part of geometry? What do they have to do with geometry? Now let's quickly understand how these tools work. What does this tool enable me to do?
Draw a circle.
Draw a circle centered at a point. What information do I need to draw the circle?
A point and length or
I need you to give me a point, and then to center it at, and then some length to set this at to draw my circle, right?
Yeah.
So I essentially need some sort of segment, and you tell me which point's going to be the center of the circle, and then I can draw my circle. That's what this enables me to do. This, we ignore the markings on it. Straight edge, forget the fact that the bottom's curved, just some straight edge. What does a straight edge allow me to do?
Make a segment.
If I got 2 points, what can I do with the straight edge now?
Draw a segment.
I can connect them with a segment, right? And if I'm careful enough, I can even shift my segment down here a little bit, reline it up, and I can extend my segment as long as I want.
Yeah.
Right? So those are the basic ways that you use a ruler and compass in an RC construction. Why are these the tools that we use? What on earth do these things have to do with geometry? Comes back to Euclid's elements. So put a pin in our geometry. We're now going to jump into Euclid's world. As though this was day 1 of geometry, and I decided, actually I'm going to teach you guys Euclid's elements rather than the book we've been using. You with me? Except we're going to skip how he starts it. He starts out giving a bunch of definitions, and then he gives his postulates. Euclid, he only has 5 postulates. We're up to 18 or whatever it is. He only has 5. What are his 5 postulates? Postulate 1. If you have 2 points, you can connect those 2 points with the segment. Notice that's exactly what this enabled me to do. What does that mean? It means in Euclid's geometry, when you are making a construction, every time you have 2 points and you take your straight edge and you use it, that is logically equivalent to you just use postulate 1 in your proof. Connecting 2 points with the straight edge in your picture is logically equivalent to using postulate 1 in your proof. Second, what's the second postulate? It was if you have some line segment, you can extend it indefinitely. You can make it as long as you want. Which again is just using this tool. So in your picture, every single time you go up to some segment and you make it a little bit longer, a little bit longer, a little bit longer, you're just using postulate 2. Again, what you do in the picture, logically equivalent to the actual postulates. His third one here is, if you've got some segment, pick a point on it, that's enough information to define a circle, which is using the compass. So now anytime you use a compass, you are using postulate 3. His fourth postulate just said all right angles are congruent to each other. We had a similar one. We said all straight angles are congruent to each other. He chose to say all right angles are congruent to each other. Doesn't really matter which way you go there. And then finally his fifth postulate. This one's a bit more complicated. I'm going to give you the logical equivalent version of it. What did Euclid say? He said, if you have a line and a point not on the line, how many lines can I draw through this point such that these two lines never intersect? One and only one, right? And that was his postulate, called Euclid's fifth. And those were his only 5 postulates. That's it. Now, he had what were called his 5 common notions. Common notions. What does his first common notion say? If A is equal to B and B is equal to C, then A is equal to C. Equality is transitive is essentially what that says. Now did we prove this one? I think we proved this one. Going way back to logic. Before that, notice we use the high level language, equals, at, equals, or equals. What were we really saying? We were saying if segment A is congruent to segment B and segment B is congruent to segment C, then segment A is congruent to segment C. Here, this is equality. Now, the Greeks weren't as precise as we are when they were talking about congruence versus actual equality. So he'll use this to also talk about congruences as though things are equal. He was a bit less precise than we are in our speech. But notice that this is not a consequence of geometry. This is logic. You can prove this from logic alone. Go back to our picture. What did I take you guys through first in this class? Logic. And then what did we do after logic?
Set theory.
Set theory. And then we went on and we actually started constructing our geometry, right? So this is a consequence of logic. Why did Euclid not include this as a postulate? What did he mean by this is a common notion?
It's more fundamental in geometry.
It's common to all fields of study. This is not something peculiar to geometry. If you're in algebra, this is a valid assumption to make. If you're studying some sort of physical phenomena, this is a valid assumption to make. It's more foundational than just geometry. It's logic. It's something common to all fields. That's what he means by a common notion. It's not restricted to geometry. And what is more foundational than logic? Nothing.
Existing.
It is what is common to every single field of study. So every single field of study is allowed to use these notions. So they're not postulates. They're more foundational than that. Go ahead.
Isn't language more foundational than logic?
Yes and no.
How do you construct logic without language?
How do you construct logic without language? You can't really communicate logic without language, and so you can't really teach logic without language. But how can your language communicate anything if it doesn't already encode logic? And so, I don't really care how you say it, one way or another. But regardless, so he says equals add to equals, here he says if things equal to the same thing are equal to each other. Here he says if A is equal to B, then A plus C is equal to B plus C. Or in other words, equals added to equals are equal. We have equals here. We add the same thing to both sides. The result is equal. Equals added to equals are equal.
Yep.
Next one. Equals subtracted from equals are equals. If A is equal to B, then A minus C is equal to B minus C. His fourth one, the weirdest one here. Things that coincide are equal. What does he mean by that? Watch me draw a triangle here. Watch me draw another triangle. Since those two triangles coincide, they're equal. That's what he meant. And then finally, the whole is greater than any of its parts. That's how he can say that an angle is bigger than another angle. if you've got some angle here, and then you split it into two, this is only part of the angle, this is only part of the angle, you go and say this has to be bigger than this, and this has to be bigger than this. How do you know that? Because the whole is greater than any of its parts. That's how you know. And so those were his 5 postulates, his 5 common notions. And now let's do some of Euclid's proofs. Going to need this to remind me what his proofs are. There exists an equilateral triangle on a given segment. Okay, his first proof. His first proof that he does is proof. Given
Segment.
AB, given AB, comma, there exists triangle ABC such that it's equilateral. So if you give me some segment, I can construct an equilateral triangle using that segment. So pictorially, what's he saying here? Here's our segment over here, AB. Given that, our job now, using these postulates, is to prove that an equilateral triangle exists, using that as a side length.
Yep.
So how am I going to do this?
You're gonna-
I can, go ahead.
With your compass?
So I'm going to use postulate 3. So let's write our proof here and draw the picture as we go. So 1, let segment AB be given. So we've got our segment. Okay, now what were you saying? Use our compass to do what?
To make an arc, to make a circle with that, with AB as its radius,
Centered where?
on A.
Centered on A. So come here and create a circle centered at A using this as our radius. Perfect. So 2, we'll say define circle. Usually you label a circle by its center point. Define circle A with radius AB. And how do we know that we can do that?
You postulate 3.
Postulate 3. Postulate 3. That's how we know that we can do that. We have to justify every single one of our steps somehow, some way. And so drawing that circle was logically equivalent to just using postulate 3. All right, now what did you want to do?
Draw another one centered on B.
Repeat, centered at B. Okay, so now we have 3. Define or construct whatever. Define circle B with radius AB. And this again is using postulate 3. Right? Okay, now what?
You're going to look at a point where the two circles intersect.
So let C be some point where they intersect. Now here's where Euclid was being a bit lazy. How do we know that those two circles intersect?
It's obvious.
Euclid would say it's obvious, and he wouldn't bother proving something like that. Now, in our geometry, that's something that has to be proved. Now it turns out that that proof is incredibly hard, and it's not a good payoff, so we're also going to be lazy like Euclid in our geometry and not prove it. But it is something that can be proved, and it is something that needs to be proved. But it's not worth it. So Euclid was onto something there. So, 4, let C be a point. Notice that the circles intersect at 2 points. We're going to pick C to just be one of those points, we don't care which. So let C be a point where the circles intersect. Okay? Now what?
Define segments AC and CB.
And they're going to be the same length.
Perfect.
Because they're both radiuses of circles.
5. Construct AC and CB. How do I know I can do that?
It's postulate 1.
Postulate 1. Postulate 1 says we can connect any 2 points with a line segment. Okay, now what?
Now you're done.
We skipped his definitions, but before he lists out his postulates, he defines what a circle is. And he defines it almost the same way we do. It's going to be the set of all these radii such that they're always the same length. So I know that AC is the same length as AB. How do I know that?
Because they're both radii.
So 6.
A.
Then AC is congruent to AB, thank you. And I know this is by definition of a circle.
Yeah.
We'll pretend, we'll just call it DC for definition of a circle. What else do I know?
You know that CB is congruent to AB?
I know that CB is congruent to AB. How do I know that?
Also by the definition of a circle. Because it's the same radius as AB and circle B.
So then we have that AB is also congruent to which one? BC? And again, that's by definition of a circle. Okay.
So now I know that CB is congruent to AC.
And now, how do I know that this side is congruent to this side?
Euclid equality is transitive.
And finally, yes, he would say 8. Then he would say BC is congruent to AC. And that is now using common notion 1. So that is because of C1.
Yeah.
And then you can finally write 9, therefore, triangle ABC is equilateral. And we're done. Being a bit lazy there, but you see all the logic, right?
Is EL an approved abbreviation?
No. That is me being very lazy right now. Okay. So there we go. There's this first proof. You just did it using Euclid's geometry. Notice Euclid's geometry is a lot more fun than our geometry. It's just looking at the pictures, drawing the pictures, and if you can draw the picture, there's a proof for it. Because drawing pictures is proving you are using his postulates. That's what you're doing. It's one of the reasons that geometry was one of the first fields developed. Is because of how pictorial it is in nature. We have such great intuition for these pictures. Just create logic that corresponds to your intuition, and your proofs come out. It's amazing. All right, let's do a second one. The second one is more complex. The second proof is proof given AB, some segment, and C not on AB, comma, then there exists D such that CD, such that AB is congruent to CD. Okay, what's he saying here? Here, we are given some segment AB, and we are given some point C, I'll draw it up here, not on AB. Our job is to construct a segment at C congruent to AB, the same length as AB. Good? Okay, how on earth are we going to do this one? Bit harder. One of the nice things about Euclid, though, is you can almost, it's very common that the next proof always relies on the previous proof.
Wow.
So I can pretty much be sure I need to use a triangle somehow, some way in this thing. And so first thing I'm going to do, I don't expect you to see how to just do this. This isn't an easy one to just look at and see as much as that one is. So first thing I'm going to do is I'm going to use segment AC, and I'm going to connect that with the segment. What postulate did I just use?
C1.
Postulate 1. And then I'm going to construct an equilateral triangle using that segment. Ooh. I don't want this line to be too close to being the same as this line. So, for the sake of our picture, I'm going to draw this one on more of an angle. It'll help our picture be more clear. You with me?
Yeah.
So, still same construction. So then I'm going to create that equilateral triangle. And so now I know that that length is the same as that length is the same as that length. Right? Now, I'm going to extend out 2 lines. First off, that equilateral triangle, how do I know I can just stick that there? Theorem 1, but for Euclid, the way he's thinking about that is the instructions for doing that, there's no point in me writing them here. I gave you the instructions right here. Go back to that and follow those instructions, and that's how you get the equilateral triangle. And then we continue on our merry way.
Right.
So maybe write out some of this as we go. So 1, what's the first thing we did?
We had AB given.
Yeah, we won't bother with that. So we construct, thank you, that's what you were saying. Construct AC. How do we know we can do that? Postulate 1. Then 2, construct triangle. We need to label this point. What should we call it? we want to save D for our final point that makes our segments congruent. So I'm going to skip ahead to E. You see why I'm skipping to E? Trying to keep what we add in different colors so you can see the initial picture. So we'll call that the point E. Okay, so construct triangle ACE such that here's how I'll do equilateral. Okay. And we know that we can do this. This is from Theorem 1. Good?
Did he call his proofs theorems?
Yes.
No, it was called the proposition that he showed is true. So they're called proposition 1, proposition 2, proposition 3. He said, and his thinking is, I propose that this is the case, and now I demonstrate it. I propose this is the case, now I demonstrate it. So if you were to Google it, you would Google Euclid's proposition 2 to find this proof.
He also had problems, didn't he?
Very likely. It's been too long. And even when I deal with it, I always deal with like rewording of stuff rather than exactly what he wrote. So I'm not sure, but logically equivalent. Okay, so now we've got that little triangle right there. What are we going to do? I'm going to extend out this line. And I'm going to extend out this line. And my goal is going to be draw a circle centered at E so that its radius is this distance plus this distance. So then, when I draw that circle, this distance will be the same as that distance.
Okay.
So extend those out. I need to find the point on here such that this is the same big as that. And then I can use that to draw my circle and get my point here such that this is the same big as that. In which case, this will be the same big as this.
Question.
Go ahead.
If you can find a point to do that, are you already done? So if you find a point to construct your circle on, right, with your...
Well, I need to be able to set up my compass here. I need a segment to set up my compass.
You could technically, can't you just draw circle A, centered on A with B as the radius?
Yes, so that's going to be, 3, extend, segments EA and EC. We can think about extending them indefinitely. It doesn't matter how far we extend them. Just extend them. How do I know I can do that?
That's your postulate.
Postulate 2, right?
Yep.
And now do what you're saying. The circle, what color will show up best for my circle here? We're kind of okay using, well, I want red to be, I think we can use blue again here, and you'll see it okay. So you're saying come to A and draw our circle, right?
Yes.
Now we only really care about this portion of the circle, so I'm only going to draw the portion we care about. Right? So that's our circle centered at A, and that's going to give us this point over here. What should we call it? F. And now, what that is making is that our purple segment here is going to be the same length as this segment. Right? Which is what we were after. Okay, so,
What's supposed to be D?
sorry, what?
What's supposed to be D? No, not
We're saving D for our point that's going to be right here,
Okay.
making that segment the same big as that.
How do we know that the circle intersects at the point F?
Because obviously, look at your picture. Good old Euclid style, that's how we know. Yeah, Euclid wasn't about all this nitty gritty, it's good enough. But let me say something about Euclid because we make a little bit of fun of him, but what he did wasn't incredible. Imagine that I went and got you a physics textbook from 200 years ago. How much of that textbook is accurate?
Not a lot.
Not a lot. Pick a biology textbook from a couple hundred years ago. Forget thousands of years ago. Let's just go a few hundred years into the past. How much of it is wrong?
All of it.
Pretty much all. A lot.
Almost go pick any textbook you want that was around a couple hundred years ago, and how much of that do we consider false now?
A lot.
A lot. Euclid's Elements is almost 2,400 years old. How much of it do you think is correct?
Well, most of it. If not all of it.
It is 100% correct. He never came to a false conclusion, even with his not so careful thinking. So he was very careful in his thinking, just not as careful as we are today. So it's amazing what he did. Euclid's Elements, 100% accurate today. You could still use it as a textbook to teach from. Nothing wrong with that.
Well, why don't we then?
we can't get into changes to education because that will take a lot of time, and I have a lot to say. Bad reasons. Well, there's some better words now. We're more precise now, so we're using largely Hilbert's axioms, which are more precise and they are better, and they're more rigorous.
Yeah.
But Euclid's Elements is easier, and it's more pictorial. And so it kind of makes sense to go this route. And it makes sense to go, I was torn when I was teaching geometry which book to use. And this geometry book that we have is just amazing.
Yeah.
But I was about to use Euclid's Elements when I started teaching until I came across this book. Because it's far, far, far better than what the geometry you got in Masada.
Yeah.
So it's a perfectly fine textbook. It's far better than the majority of textbooks out there. We just happen to have a geometry textbook that I really, really like. Okay. Anyways. So what did we do next? After we extended our segments, we did construct circle, A with, what did we use as a radius?
AB.
AB, that's using postulate 3. Good. Now we said 5. Let F be where circle A intersects EA's line. Being real lazy in my speech here for the sake of space. Because we extended a line through EA, right?
Right.
That was one of our previous ones, so that's the point F. Okay, so now I got my point F there. Now I'm going to, well, let's see if one of you see it.
You're going to draw a circle E with EF as your radius.
Perfect. I may now use this as my radius, draw a circle centered at E, and that's going to give me some point where it intersects up there. Maybe we're okay with purple. So I'm going to come draw, very hard to. Maybe like a guess where it should end and then try to draw my arc from there. So the circle we care about is a circle that comes something like that, right? And so that was the circle centered at E with radius EF. Sorry, put 2 ticks through these lines, because the 1 tick lines are the equilateral triangle, right? So 2 tick for those lines. Okay, and so now we get this segment. Maybe we're okay. Now that's what we were after. We'll draw it back in red. And we're going to call this point up here the point B. Right? Okay. Now, make our argument in logic, but our argument is going to be that that is the same big as that is the same big as that. So that's everywhere where we're going. So next, continuing with our argument, what was the next thing we did?
We had to label D.
We needed to
Yeah, draw that.
define circle, or construct circle. Construct circle, circle what? E with what radius?
Yeah.
With EF. And that was using postulate 3. Good. And now, what did we do next?
You define D as the point where circle E intersects
DC's line.
C's line.
Let D be where circle, what circle?
E.
E intersects line, what was the line?
E
The one that we extended using E and C, right?
Right.
Okay, so now, what do I know? Then, I know that ED is congruent to EF.
Which means that CD is congruent to AB.
ED is congruent to EF. How do I know that?
Because they're radii.
Definition of a circle. So we get that from definition of a circle. What did I do before? D dot C for definition of circle.
DC something.
All right. So that gives us that. Then I need to argue that AF is the same big as AB. Forgot to say that somewhere before. Oops, I put these above. Sorry, in some textbooks, when they want to talk about a segment, they put the line above it. In this class, that means the length, so don't let me do that. We also have then AB. AB is congruent to AF. That was also by definition of a circle. Those were both radii of the circle centered at A. Okay. Now, what are we trying to argue? Then, I know CD is congruent to AF. How do I know CD is congruent to AF?
Combination of 3. Equals subtract from equals equals.
CD is congruent to AF. Right, I know this whole thing is congruent to this whole thing. Since this is an equilateral triangle, that's congruent to that. Therefore, that's congruent to that. So we're using common notion 3. Equals subtracted from equals or equals is the way Euclid would say that. So this is using common notion 3. And now, finally, 11, we get, therefore, CD is congruent to AB. And how do I know that one?
Combination 1.
Common notion 1. Things equal to the same thing are equal to each other. Give you a taste of Euclid there. Do a couple more. We'll stop writing out the proof. Now we'll just do the picture. But you see how doing the picture and writing out the proof are almost logically equivalent with Euclid. It's exactly what you're doing. They're the same thing. So we can just do the pictures. All right. This next one, I think it's the next one. Yes. So if I have two uneven segments, if I have a segment AB and some smaller segment, CD, Euclid says I can cut off a portion of this segment congruent to this segment.
How does he define smaller?
With your eyes.
Okay. Alright.
So, how can I cut off from this segment a portion congruent to that segment?
Using the same construction you did before.
Using what we did before. What do I know I can do from this? This says, pick a segment and a point. You can construct the segment with the same length.
Yeah.
So here's a segment. Here's a point. So what do I know using this theorem?
That you can construct the segment with the same length.
That I can now construct a segment. I don't know which way it points, but I can now construct the segment AE so that this is congruent to that. How on earth do you do that? You re-go through this step. I would connect these 2 points. I construct my equilateral triangle here. I construct my circle there, and then my circle there, and then my big one.
Yeah.
Oh, there wasn't another one there, just a big one. But, so you could go through those steps again. Copy, paste, throw those steps in. That's how. Okay, so that gave us that. Now what do we do?
A circle centered around.
Just draw a circle at A centered at, or draw a circle at A with radius AE. That intersects right here. That is the same length as that. So, AF and AF is going to be congruent now to CD. Much easier. These proofs are not all equally hard. Some are much easier, some are much harder. His next one, he proves his side angle side for congruency. We had to use a side angle side postulate. How did Euclid come at this without a postulate? So he says, let's look at 2 triangles. Don't read too much into my picture here. But we have these 2 triangles, A, B, C, D, E, F. He said, if you know that this side length is the same big as that side length, you know that angle is the same as that angle, and this side is the same as this side, then you know that the 2 triangles are congruent. How do you know? Here's the way he says to do it. He says, look, pick up this triangle and place it so that A is right here on D. So I'm going to take this point, I'm going to drop it right here. So that's also now the point A. You with me?
Yeah.
And line up this segment so it follows this segment. Where does B have to land? B has to land on E since these segments are the same length. So E is going to be the same as the point B. And it's going to land exactly like this. Now, where is this second segment going to land? It has to land along here since that angle is the same as that angle. So that second segment has to land right here. And where does C have to land?
On F.
It has to land on F because this segment's the same big as that segment.
Right.
And so the 2 triangles perfectly coincide. And of course, things that coincide are equal. So those triangles are equal to each
What
other.
about the bottom segment? What's the logic that AC lands on BF?
They have the same start and end point. There we go. Side angle side. A lot easier, right? Just pick it up and move it. What's so hard about that? Okay. Let's see.
How does he define an angle?
He's not letting it go to my. It might not be defined much different than us in terms of rays. He might have just done it with segments and not extend the ray all the way. I'm not sure. Because it's definitely the case that we call it a triangle because it's three angles, because he thought about it as three angles rather than being three-sided. It is weird. We call it a triangle rather than a trilateral.
Yeah, I guess so.
But if it's four-sided, we call it a quadrilateral, four sides. We don't call it four-angled.
Pretty good.
Yeah, names you can call it whatever you want, but just an accident of history that it comes out the way it does. Okay, his next one was in an isosceles triangle. We have enough room to scribble over here. We'll scribble to the side here. In an isosceles triangle, what do I know about isosceles triangles?
Base
They have two
angles
sides
are
that are the same.
the same.
So far, we don't know the base angles are the same. We're in Euclid's geometry. We haven't proven that yet. That's what we're about to prove. But he proves that two things. Let me extend these down and you'll see why here in a second. He says in an equilateral triangle, we'll call it ABC, the base angles are congruent. So we need to prove that the base angles are congruent. And, I can't remember what he calls them, but these angles underneath the base angles are also congruent.
For an equilateral triangle?
In an isosceles, did I say equilateral? I meant isosceles. Let me read what I have written here. In isosceles triangles, the angles at the base equal one another, and if the equal segments are produced further, then the angles under the base angles are equal to one another. That's the way he phrased it. Okay, so I'm trying to prove that this angle is congruent to this angle, and then this one's congruent to this one. Good?
Yep.
Now, first, how can I prove that this angle is congruent to this angle? That's the easy one. Euclid says that we have that by side angle side. By side angle side, triangle BAC is congruent to triangle CAB. And therefore, its first angle is congruent to its first angle. It's exactly the way we proved it in our class. Just see the same triangle two different ways. Or see two triangles in the same triangle, I should say.
Yeah.
Alright, so that's how you get those ones. Those ones are easier. Now, we need to prove that the base angles are congruent to each other. How do we do that? So for that one, we're going to come and we're going to just pick a point, any point, on this extension here and call it D. Good? Now, I know how to mark off a segment congruent to this segment over here. So I'm going to come mark off this point over here, E, so that this is congruent to that. Obviously using what we did here. Good? Okay. Now, look at, should have marked this one. Let me do these ones as the two ticks, and then these ones as the one tick, since it's an isosceles triangle. You guys me? Now, I'm going to draw two lines. We can still do it with purple, it's fine. And we're going to look at two triangles. The triangle that we're looking at is, I'll draw one over here. We're looking at triangle ABE. ABE. And we're looking at triangle ACD. You see both those triangles? ABE and ACD. You see the two triangles?
Yeah, we see.
How do those two triangles relate to each other?
They are congruent.
They're congruent. AC is the same big as AB. AC, AB. CD is the same big as BE. No, sorry.
BD is The same big.
Let me label these better, so I put the angle in the middle. I'm saying that triangle, now I can't remember which triangle I drew over here. I'll do the one with the longer side over here. So I'm going to call it triangle, I'll call you DAC. So this triangle, is going to be congruent to triangle EAB. And it's going to be congruent by side angle side. DA is that side. That's the same big as EA. Angle A is the same big as angle A. And then AC is the same big as AB. So DCA, or sorry, it's not right triangle, but say it the same way I labeled my points. DAC, this triangle, is congruent to this triangle, EAB. You see the two triangles? And so, their angles are congruent to one another. All their corresponding angles are congruent to one another. In particular, black here, this angle is congruent to this angle. You see it? Is that the one I want?
No, wouldn't you want to say using C3 that angle ABE is congruent to?
I have that. Oh, and I also have, let me use 3 tick marks. Purple line here is congruent to purple line here.
Right.
You see that?
Yeah.
And now we're looking at these smaller triangles. This triangle, CEB, this one, is congruent to this one.
There you go, there, 90 angle.
Which gives me that their corresponding angles are congruent, which gives me finally that purple angle here is congruent to the purple angle here. You see that?
That's how you prove that.
The angles underneath the base angles are also congruent.
That an angle supplement is, if two angles are congruent, then the supplements are also congruent.
Well, that's more general. And so we could have gotten that for free. We showed that if two angles are congruent, then their supplements are also congruent. Which is how we would have done it in our geometry, but we don't have that proof yet. So I'm just giving you Euclid, a taste of Euclid's way of proving these things. Good? Okay. So RC constructions now. Let's go to the next board. The author does some constructions in the book. Now, once the author starts constructions, you don't have to do those homework problems. I'm not going to make you do any construction problems. Something tells me you guys still have a bit of work with chapter 6 to do. Just a hunch. Which is understandable. So chapter 7, I know we're covering a lot today, but you'll only really have to deal with the stuff that we covered right at the start. The rest of this is just to give you a feel for geometry more generally and what existed historically speaking. Let me steal some of these. Purple was doing pretty good. One of the reds was good. Can't remember which red. And green over here is okay. Oh, there were 2 more problems I wanted to do Euclid's way. Just drawing the picture. So I want to reprove our first theorem, Theorem 7.1, Euclid's way. So this first theorem here, I want to redo that one Euclid's way really quick. So we're going to do the proof that the exterior angle is bigger than either of its opposite interiors. So setting up our picture, I'll try to follow convention of setting up the picture with red really quick. We're going to be a bit messy and go a bit fast here. So A, B, C, not sure if I labeled it the same as over there. I'm going to show this angle is bigger than that angle. And you can do the same thing to show this angle is bigger than that angle. Just redraw your picture. Okay, so what's the Euclid way of doing this? The way Euclid does this is pick your midpoint here. We didn't talk about how to find a midpoint. That's something we'll do in our constructions here, but there's a way to find a midpoint. Pick the midpoint there, so that this is congruent to this. Draw your segment through that point, and extend it far enough till you get some point over here. Try and do somewhat okay picture. So that this is congruent to this. C, we'll call this a point D, and this up here the point E. With me? Now we get this new resulting triangle. over here. And this triangle over here, DCE, what's it congruent to?
CDA.
Not CDA,
ABD and
ADB, right? Because these are vertical angles. So by side, angle, side, angle, side, this triangle is congruent to this triangle. Which gives me, what is angle B congruent to? It's congruent to this bottom one right here. So that gives me that this is congruent to this. The whole is greater than any of its parts. Part of it is congruent to that. Therefore, the whole is bigger than the part.
Is the triangle DEC also congruent to triangle ABC?
Say it again.
Is it triangle DEC also congruent
DEC congruent to?
to ADC?
No. This angle is not the same big as that angle
But
necessarily.
it's halfway the.
I could have drawn this up. Those were both 20, and these were both 70. Let me draw the picture a differently for the exact same proof. That didn't work, did it?
because it's a midpoint.
If it's a midpoint, aren't the triangles the same?
No, they're not going to necessarily be the same.
I don't think so.
How could I draw it so that it is more obvious?
Whoever proves it is the
Would it be more obvious if I made it more vertical? So let's say our triangle started like that. So our midpoint would go like this. I think that shows a bit better. So the taller I make the triangle, the more vertical, then you can see that these are going to be bigger and these are going to be smaller.
Oh, okay.
Okay. Didn't jump out as much. I was stretching the wrong way. Rather than stretching this way, I should have stretched vertically. Okay. Anyways, so that's how he does it. Pretty nice proof. One more I want to show you guys is Euclid's way of doing the Pythagorean theorem. We haven't done the Pythagorean theorem yet in this class. That will be in the next chapter. But Euclid's way of doing it, this pictorial way, is very nice. And it gives you another feel for the way that the Greeks thought about geometry. So what does the Pythagorean theorem say?
A squared plus b squared equals c squared.
No, it says the square on two.
You're going to get something thrown at you. It says if you have a right triangle, such that the side lengths are A, B, and C, where A and B are the lengths of the legs, this has to be a right triangle. Then the associated squares you can make, if we built this square, we built this square, and we built this square, then the area of this square plus the area of this square will exactly equal the area of that square.
Yeah.
Right? Let's draw Euclid's proof of it. Really quick, we have to use the fact that the angle sum of a triangle is 180 degrees. How did Euclid prove that? We can't prove that yet because we don't have parallel lines. You need parallel lines to do it, but we'll do this one pretty quick. So I need to show that the angle sum of this triangle is exactly a straight angle, 180 degrees. So the way we're going to do that is we're going to do the line through there and then build the one and only one line through here, parallel to this line using postulate 5 there, right? Now, extending these purple lines up here a little bit. This angle is congruent to this angle. This angle is going to be congruent to this angle. And then this angle is going to be congruent to this angle. And so, this angle plus this angle plus this angle is the same as that plus that plus that is a straight angle. So the angle is 180 degrees. Okay, so Pythagorean theorem now. How do we prove this one? We're going to draw the same picture two different ways. So here's the ways that he drew the picture. Try and not be too terrible. I'm trying to draw the exact same square twice. So that's meant to be a square. label some points on it. I'm just going to label the distances. I'm going to call the distance from here to here A, and this distance B. With me?
Yep.
And once again, similar thing. A, B, A, B. Go ahead.
Sorry to interrupt. We'll need to talk to you sometime in the next 5 minutes.
The next
Or
5
about
minutes?
5 minutes.
Okay.
There's 15 minutes for about 5 minutes.
Okay. So there's those. Now I'm going to do a similar thing over here, but I'm going to have my points line up like this. A, B, A, B, A, B. Now I'm going to draw some connecting lines. And over here, I'm going to draw these lines like this. Good? Now what is the area of a square?
It's your side length squared.
It's a side length squared. What is the area of this whole square?
AB squared.
It's A plus B, whatever that side length is, squared. That's why we call that squared. It gives you the square with that as a side length. So the area of this square is A plus B squared, and the area of this square is A plus B squared. So they have equal areas, right?
Yep.
Now, what is the area of this square? Let's break it down into its pieces. What's the area of this piece?
AB.
Maybe we'll do that in purple here. So the area of this piece, the area of a rectangle is length times width. What's the area of this?
This width. AB. B squared.
Perfect. And now, over here, we need to make some quick arguments. This is a square, so I know that this is a right angle, right?
Yeah.
Now, this angle right here, I'm going to call it alpha. This angle right here, I'm going to call it beta. You with me? Alpha plus beta has to equal 90 degrees. Because the angle sum of my whole triangle is 180. So if alpha plus beta plus 90 degrees gives me 180 degrees, then alpha plus beta by itself has to be 90 degrees. This isn't how Euclid argued it, obviously, but I'm trying to give you the fast version. But I know alpha plus beta has to equal 90 degrees, right? Now, notice that this triangle is congruent to this triangle, is congruent to this, is congruent to this by side angle side, because these are all right angles. You see that?
Yeah.
So this angle right here is also, what's this angle? Alpha. So, if alpha plus beta is 90 degrees, what is this angle right here?
90 degrees. So it's right angle.
This has to be 90 degrees. Because all three of them together have to be 180 degrees. Now I'm saying degrees to help you think, but the point is, all three of these add together have to be a straight angle. Alpha plus beta plus 90 degrees is a straight angle, so alpha plus beta plus that has to be a straight angle.
So,
Or that has to be a straight angle, so that has to be the same big as that.
Okay. Yeah.
You think you got it?
yeah.
A similar argument for, and that is a right angle, and that's a right angle, and that's a right angle. And since all these are congruent, that this side length is the same as that, is the same as that, is the same as that, call it C. We'll label C here above the red. All that argument is just to say that this internal shape here is in fact a square. That's the whole point of that little argument there. Okay, so now let's look at the areas. So over here, notice what we had as its total area. Its total area was we had a squared,
It's 2AB.
plus we had two of those, 2ab, plus b squared. And then this thing's area, let's count it up. What's the area of this triangle?
It's
180.
The area of a triangle.
It's
180.
AB divided
Half the
by
base times the height.
Yeah.
So it's going to be 1/2 AB, but how many of those triangles do we have?
4.
4, so count that 4 times. Plus, what's the area of the internal square here now?
C squared.
C squared. So these two have to be equal to each other. What's 4 times 1/2?
2.
So 2ab, cancel those out on both sides, and we get c squared is equal to a squared plus b squared.
And A squared and B squared are the legs of a right triangle.
Where a and b are the lengths of the legs of a right triangle. And c is the length of the hypotenuse. So if you take a right triangle, that square right there, c squared, is exactly equal to the area of that square plus the area of that square.
Yeah.
Make sense?
Yep.
Okay. So, we're that, I guess I have to go have some conversation. Put a pause in the lecture, and then we'll just do some more constructions and see the limitations of Euclid's elements.
Can we take a break?
Yeah. All right. Let's. So we got a good taste for Euclid's elements. That's as much as we're going to dive into Euclid's elements. The point is, the author spends a lot of chapter 7 introducing you to what are called RC constructions. What's an RC construction?
Ruler compass.
Ruler compass construction. It's what Euclid was doing. He tries to give you an idea of why it's historically important. That's why it's historically important. So I did a much deeper dive than the author touches on into Euclid's elements to help you understand why they were so important. You were literally using Euclid's postulates. Drawing the picture was the same thing as constructing your proof. Now, famously, the Greeks had 3 problems that gave them a lot of grief. First one was trisecting an angle. Not bisecting it, trisecting it. If I give you some angle, do Euclid's postulates allow us to trisect this thing, split it into 3 equal pieces? So split it into 3 pieces such that that angle is the same big as that angle is the same big as that angle. So trisecting an angle. Seems like it should be possible. We definitely want to be able to do that in our geometry, right?
Yeah.
And it turns out using Euclid's postulates, you can't ever get that.
Really?
Yes. So this was a problem one of the problems that the Greeks were stuck on for forever. They couldn't figure out how to trisect an angle. Turns out there's a good reason they couldn't figure out how to do it. It's because their geometry didn't allow for it. So we prove everything Euclid's elements proves, but our geometry, in being more precise and opening up our postulates more, we can prove more than what Euclid proved. Things that Euclid definitely wanted to be true in his geometry, just couldn't figure out how to come up with the construction for it.
Why can't you construct a proof for that?
It is physically impossible. Only using a straight edge and compass to trisect an angle. Let's bisect one really quick. So bisecting is trivial. So really quick, let's say I've got some angle here. Imagine that you are constructing some figure. I don't know, you've got this corner here. Your job is to construct a wall that perfectly splits down these 2 walls, whatever it is. You've got to trisect that angle. You've got to perfectly do it.
Bisect?
Or bisect the angle, thank you. So how do we do this? First thing we're going to do is we're just going to take our point and we're going to draw a circle with radius, who cares?
Right.
That's the exact radius we use. So there's radius, who cares? And it gives us this point and this point, right?
Right.
And so I have that this length is the same as this length.
Yep.
Now, being a very important radius, we use radius, who cares again, to draw a circle centered here. And that's going to give us some point, some curve, some part of the circle will lie here. I'm going to come here, draw the exact same circle, and those 2 circles are going to intersect at a point on that side. And so that will give me that this side and this side will both be radii of those circles, or in other words, this will be congruent to this. You with me? Finally, connect these 2 points with a line segment. Sorry about the curve. Now, what do I know? This triangle is congruent to this triangle by side, side, side. Which means that this angle is congruent to this angle. And so that is in fact the line that bisects the angle. And now I could bisect this angle real easily and bisect that angle real easily. So I can split it into 4. So splitting it into 2, easy. Splitting it into 4, easy. Splitting it into 8 after that, easy. 16, 32, etc. So those are trivial. And you can come up with other clever ways of breaking up into other numbers. Question is, I just want to break up into 3 equal pieces. How on earth do I do that? And provably now, you cannot do that with just a compass and a straight edge.
Why?
I have never gone through that proof, so I can't even begin to give you the intuition for the proof. But I can tell you that the proof is not going to have an easy, here's why. But notice that compass and straight edge is kind of all Euclid's postulates give us. So in Euclid's geometry, you couldn't trisect an angle, which is something we want to have. So our geometry is in some sense more powerful than Euclid's. We don't do anything there's nothing Euclid does that we can't do. We do everything Euclid did, we just do and then some. Because in our geometry, we definitely can trisect an angle. How you construct it with a compass and ruler, you can't, who cares? but we could definitely talk about trisecting an angle in our geometry. The other one they had is called the duplication of a cube. How does that one work? I give you some cube. For the sake of keeping this simple, we're going to say that the length of the cube is 1 meter. So this cube is 1 meter by 1 meter by 1 meter. What's the volume of the cube? 1 cubic meter. Now, I say, I need you to construct me a cube now. And the goal of our new cube, that was awful. The goal of our new cube, it has side lengths, length, width, and height x. But whatever it is, I want this new cube to be exactly double the volume of my existing cube. Now, what would x need to be here so that its volume here is 2?
It's volume.
2? Yeah, you just double it, right?
2 cubits.
What's 2 times 2 times 2?
8.
8. Okay, so that doesn't work. Right? If this box holds 1 cubic meter of water, and then if I take it and I double its length, double its width, double its height, I made the volume 8 times bigger. I just want to double the volume. I want to find the cube that just makes the volume twice as big.
Have 2.
So that the volume is 2.
Like,
It's a
Could
cube
do
root of 2.
1.25?
What's a cube?
1.25, it would get you closer to it, but that's not going to come out to exactly 2.
It's just a cube root of 2.
It's the cube root of 2. Look, we're looking for x such that x cubed is equal to 2.
I see.
Take the cube root of both sides, we get x is equal to the cube root of 2. So the problem is logically equivalent to, if I give you some segment, use a ruler and compass to construct a segment whose length is, if this is length 1, construct this so that this is the cube root of 2.
Yeah.
It's logically equivalent to doing that. Turns out, an impossible problem using a ruler and compass.
Yeah.
Square root of 2, super easy. Cube root of 2, really, really hard.
What do you mean?
So hard it's impossible. What do I mean square root of 2 is real easy?
Yeah.
Let's draw a square. And let's draw a square and we'll call the side length 1.
Oh, you're right.
What's the diagonal of the square?
Square root of 2.
Root 2. Pythagorean theorem. 1 squared plus 1 squared equals 2 squared. 2 squared and 1. I was thinking of should I put a 1 there or not. 1 squared plus 1 squared equals the square root of 2 squared. Because 1 plus 1 is 2. So square root of 2. So constructing square root of 2, that's trivial. Constructing the cube root of 2, impossible. You can kind of see some sort of relationship here and here. Something with these 3's makes it harder. What was the final problem that they tried to do? Notoriously famous one. You may have even heard of this one. They call it squaring the circle. What's that problem? The problem is I give you a circle. There it is. It's beautiful. Your job now is to construct a square with the exact same area.
Yeah.
Now, that doesn't mean find a square that contains a circle. That's stupid easy. Anyone can do that. It doesn't mean to find a square that fits inside the circle. It means find the exact square whose area is equal to the circle. And it turns out, once again, impossible. And that one was actually kind of common in Greek culture. There would be expressions along the lines of, you may as well try squaring the circle. Like, what you're trying to do is impossible. Now, they didn't know it was impossible. It took modern mathematics to prove that these things were impossible. So they had no clue, but what they were doing was impossible.
And why exactly is that possible with straight edge over those straight edges?
I don't have the proof for it. But I'm guessing that they came up with a way of corresponding constructions with certain types of algebraic functions, and then showed that these correspond to non-algebraic functions, and that those only give you algebraic functions, or something to that effect. I'm not sure. But it's not going to be some straightforward, here's your intuition, don't it feel good? If it was intuitively obvious, they probably would have seen some connection. Anyways, so there's those 3 problems. Impossible problems. For them, impossible in Euclid's geometry. So Euclid's geometry is in some way wanting. Our geometry doesn't have that problem. Okay, now some other constructions that the author does. Just take you through them. To copy an angle, copy a triangle, create a perpendicular. We don't need to copy an angle because copying a triangle, you have to copy an angle. So I'll just show you that construction. So here's the problem. The problem is I give you some triangle. ABC. Did I start my recording again?
Hope so.
I think so.
Yeah, it looks like it.
Yes, I did. Okay. Phew. The problem is, now I give you some ray here. Reconstruct this triangle on this ray. I'll call this a point A prime, so I want that point to land right there. Okay, how are we going to do that? We can use what we've already proven in Euclid's element on top of that, anything else we want.
So you're gonna construct a segment that's congruent to AC.
So we can mark off, yep, we can see where C prime is going to lie. That's real easy because we know how to draw a segment with the same length at another location. So we can do C, call C prime right there real easy. Now what do we do?
You're gonna have to copy an angle.
Yeah, but we don't know how to copy an angle
And
yet.
then can you do a circle centered on A prime with AB as the
Perfect.
radius?
Do a circle with this as its radius centered here. Yes, we can do that. That's our second proof, is that we can come here and we can construct a segment congruent to any other segment at the point we want. Number 2 tells us how to do it. Use that segment to construct a circle. I'll try and do it half decent, but no promises. So there's our circle using AB. Do the same thing now for C, right? And its circle, and those circles are going to intersect at some point. That is going to be congruent to that. This is going to be congruent to this, and obviously this is going to be congruent to this, and so those triangles are congruent by side. Now, again, these are very physical processes. So for the Greeks, imagine that they had some geometric, you could take some geometric figure and often reduce it to a bunch of triangles, right? So imagine that we had some structure over here, and we wanted to go exactly 200 meters that way and relay out the exact same structure. And they were very physical processes using strings and using long pieces of wood, extending points, trying to figure out how to do this. And the steps that, if you walked from a bird's eye view of them taking, it would be very similar to going through the steps of all these constructions. And that's exactly what you would watch them carry out. It's very practical for a long time to know your geometry if you were going to be any sort of an architect. Or even drafting, when drafting was done by hand. Now computer programs help you do it. A lot of draftsmen need to know a bunch of basic ruler compass constructions to help them construct things. So there's copying a triangle, perpendicular bisector. Okay. For this one, we've got some segment here, AB, and we want to construct its perpendicular bisector. We want to construct the bisector, so a line that is at 90-degree angles with it, it's perpendicular to it, and goes right through the midpoint.
So you're going to start with the circle centered on A with B, AB is the radius. And then same with centered on B.
That was awful. Let's try this. And then same thing on B.
And then draw a line through the points where the two intersect.
So then draw the line through the two intersecting points. And now we've got these triangles, right?
Mm-hmm.
These are all radii of the same big of circles, so I know all those side lengths are congruent, right? And now I know that bottom triangle, well, do I care about that? How's the best way to see this? Yeah, bottom triangle, bottom isosceles triangle is congruent to top isosceles triangle, which means this angle is congruent to this angle, but also this one's congruent to this one, and is also congruent to this one, so all those angles are congruent.
Right.
You see that? And now, looking at the smaller triangle, this segment is obviously congruent to itself. So side angle side, these two are congruent. And so supplementary congruent angles are right angles. And so that's a right angle. And then flip it over. This is also going to be congruent to this, so that's the same big as that. So this is the midpoint because these two segments are congruent to each other. And that is a perpendicular bisector since it has a right angle. So there's our perpendicular bisector. Nice. Okay, next one we want to do is perpendicular to a line at a point. So now, this time I just have a line, some line L, and pick some random point P on there. Now what do I want to do? I want to construct a perpendicular bisector at P. How can I do that? At P.
Can you just choose a radius?
Sure. We had a special radius. What was our special radius?
Who cares?
Yeah, so we use who cares over here, and we construct a circle. And it's going to intersect at these 2 points A and B, right? And now we do exactly what we did over here. We construct the perpendicular bisector of A and B. I didn't do that very well. P is supposed to be the midpoint there. And that perpendicular bisector will go exactly through P. So just repeat those steps.
Maybe that same, like, kite-ish look.
Yeah.
Yeah, if we went through the construction.
What's the main difference?
This one went through the midpoint of a segment. This one, I had some line. I picked a point. And now I want to construct a perpendicular bisector there. What did you do? You just need to create a segment really quick that it was the middle of. And now the perpendicular bisector will go through that midpoint. Let's do one a bit more tricky. This time we're going to have a line. And P is going to be up here. Oh boy. I want a perpendicular bisector that goes through P.
So choose a radius on the line. Choose a radius on the line
Yeah,
that meets P.
Choose a radius on the line that meets P.
Yeah.
So we got to take it from some point.
Right.
So I'm going to pick some point A here. Okay, so now I use this to construct a circle is what you're saying, right? Something. Okay.
And then you're gonna choose, so B, let's see, C is your point where your circle centered on A.
I would do the point that the circle intersects, you could have B, and then you can do another circle.
On the way.
Oh, yeah.
Do what?
So you're just gonna, you're going to center another circle where the first
Center it
circle
where?
intersects L. With,
Over on, okay.
Tell me where my starting point is.
Intersect B,
Huh?
where it intersects the line B.
That's
the
the
point
point.
C.
You're saying right here.
Yes, and then do a.
So I'll call that the point B. Cool.
Do a circle from
centered
B,
on B, the
radius of P, B.
AP.
So B to P, do a circle. It's going to have a different radius. Those aren't necessarily the same circle.
Yeah.
Okay, so we got that.
That doesn't look right.
Then it's to, is it to a radius of like A?
Okay.
Yeah, I'm confused.
Yeah, you guys were hoping that that would somehow magically come out centered.
Yeah.
Yeah.
And it isn't behaving with you. So, next thing.
You kept your last circle.
Sugar. Alright. Back to our first circle. You're on the right track here. P. Here's our first circle. Actually, what you guys did is fine.
Yeah, but you can do the radius like B.
Let's do that again, and we'll keep that on there. So,
Is that
Not-
radius BP?
quite the same with BP, yep. So, we've got, we'll just draw some triangles now. Do. And then we have where those points intersect down here. Wherever they intersect. I'll try and make it line up better for how it should be rather than how my dots may come out. We'll call this point down here the point P prime. So we got that. And so far, what do we know now? We know that this length is the same big as this length.
Yeah.
And we know that this length is the same big as this length.
Yes.
Yes.
So that's what we have so far.
Yeah.
And
Those
then
two
by
triangles
side,
are
side, they're congruent triangles.
By side, those are congruent. But we're looking for the perpendicular, so obviously let's drop this line. Right, that's screaming to be dropped. And now we need to somehow argue that that line is in fact perpendicular. Now you saw side, 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 and so that gave us that this angle was the same big as this angle. You see that? Okay, so now what do you see?
That APB
Right,
is
so on the
like,
other side.
APB is isosceles, so that you have
ABP, not isosceles.
That's not.
Two different
I was
radii.
gonna say by side angle side, then the triangles are congruent on that.
What's congruent to what? Let's label this point O.
Yeah.
But you can talk.
Okay.
Sorry.
APO is congruent to AOP.
APO is congruent to AP prime O.
Yeah.
P prime, sorry.
That's-
Make sure you get the order right. So we got, and that's by side angle side. And so these are supplementary
Congruent angles.
congruent angles. So they're right angles. So it's a perpendicular, and it went through point P.
Right, and then the same goes for the other side.
Well, we're done. We were just trying to find a perpendicular line that goes through P.
Yeah.
So we picked the line that went through P that we thought would be perpendicular and showed that it was in fact perpendicular. Cool.
Awesome.
We already did angle bisector, so that was all the constructions that the author does in the book. So that is it. Next week we will be starting chapter 8, which introduces our last postulate, the parallel postulate.
Awesome.
Making good progress. Go ahead.
What is going on with the midterm? I'm not, does semester end?
Okay, let's end lecture and talk about whatever. No, the semester ends after the break.